So welcome to my seminar presentation. Today I will be presenting three recent works in the field of versatile skill learning and robots. And the contents of this talk will be first, I'll name the papers that I'll be presenting, then the background on Soft Actor-Critic, why we should learn skills and what are skills, mutual information, and the formulation of the mutual information objectives in the three papers. Then I will show how the three papers facilitate diverse skill learning, and then I will show two examples of what skills are learned by the robots. So the three papers that will be discussed in this presentation are Diversity is All You Need by Eysenbach and others from 2018. It introduces a concept of learning diverse skills without an environment reward. Then One Solution is Not All You Need, which encourages skill learning by adding a diversity bonus to the environment reward. And finally, Discovering Diverse Solutions in DeepRL by Oza and others. Here, the diverse skills are learned with a separate objective. So we're dealing with a reinforcement learning problem, which is defined as a Markov decision process represented by the state space S, the action space A, the state transition probability P, the reward R, the discount factor gamma, and the initial state distribution psi. And the goal is to maximize the expected reward. All three works base their algorithms on the Soft Actor-Critic algorithm by Harnoya and others from 2018. And Soft Actor-Critic adds an entropy bonus to the policy objective so that the policy entropy is kept high, which means that the uncertainty of which action to take should be kept high, so that when the agent is in the state where multiple actions promise high returns, the algorithm will not constrict the policy to always choosing the same action in that state. And as you see, the inputs, the state action inputs are added, an additional input is added, which is the skill vector Z, and that is a prerequisite to learning skills. These are sampled from a uniform distribution during training and can be set during test time to elicit different behaviors in the agent. So why should we even learn skills? Learning diverse skills allows an agent to learn multiple modes of behavior, and this can make it robust to perturbations of the environment. For example, if we train the agent in an unperturbed environment, the agent might then be well suited to achieve a high reward when, for example, obstacles are given or forces are applied to the joints, or there are any motor failures in the agent. So what are these skills? Well, the skills are the elements of the latent variable vector referred to as skills, and there are discrete and continuous ones. Discrete skills are represented by a one-hot encoded vector. So for example, 3 discrete skills with the second one active will look like this. And at the beginning of each episode, a new discrete skill is sampled. And each discrete skill makes the agent visit different parts of the state and action space, depending on the algorithm. Continuous skills, on the other hand, are a set of independent continuous variables, and they are sampled from a uniform distribution in -1 to +1 at the beginning of each episode. And this is how a continuous skill vector could look like. Eysenbach and others, and Kumar and others, only use discrete skills in their algorithms. And Osa and others, they introduce continuous skills to the picture and often mix both together. And this is simply achieved by concatenating both vectors. And the way that these skills are learned is through mutual information. And to give a short introduction to mutual information, the mutual information measures the information that X and Y share. It measures how much knowing one of these variables reduces the uncertainty about the other. And properties of the mutual information are that it is always positive, it is symmetrical, and it can be expressed in terms of entropy. And extremes are when x and y are independent, the mutual information is 0, and if x is a deterministic function of y, the mutual information becomes maximal. Now, how do we use this mutual information to actually learn the skills? This must be defined over an objective. And here there are two different approaches. For one, we have the approach by Eysenbach and others, which is also used by Kumar and others. And here, the information is formulated as such. They want to maximize the mutual information between the skill and the state, so that the skills determine the states that the agent visits. Then we want to have a high entropy for the action given the state, and it should be made sure that the skills are distinguished by states and not by actions, and so we minimize this mutual information term. And this gives us the mutual information objective, J1, which should be maximized. Eysenbach and others, on the other hand, take a different approach. They want to maximize the mutual information between the skill and the state-action pair, so that the skill determines not only which states the agent visits, but also which actions it takes. Rewriting these mutual information objectives in terms of entropy gives us equations 1b and 2b, and rewriting the entropy term as an expectation of the log probability gives us this. And now we have a problem, because the distribution here is the posterior distribution of the skill given the state or also the action. And it cannot be calculated directly. It is intractable. So what both approaches do is they approximate it with a discriminator. And in Eysenbach's case, it looks like this. And this lower bounds the objective because entropy of the discriminator will always be higher than the posterior distribution. And the first entropy term here is already implemented in SAC because the entropy in Soft Actor-Critic, the entropy of the policy should be kept high. So we can actually drop this first term, and this further lower bounds the objective. Now, Eysenbach and others, they do the same approach. They approximate the posterior distribution with a learned discriminator, and we receive these two equations. Now, even though both approaches started out with very different ideas, they both end up with a very similar objective, which only differs in that also include the action. So now we need to somehow bring this objective into the reinforcement learning algorithm. In Eysenbach and others, the objective is simply set as a reward. So the agent does not receive any environment reward during training, but simply only gets the objective as a reward. And here the entropy term has a further benefit as it keeps the reward positive. And without it, the agent would end the episode as soon as possible, which in most environments we don't want, except for some like mountain car, where we actually want to end this episode as soon as possible. Kumar and others, they build on top of Eysenbach's approach, but actually give the environment reward during training. And they have the following idea, which is give the environment reward, and as soon as the accumulated reward surpasses a certain threshold, we add the pseudo reward from Eysenbach and others as a bonus. And this requires us to know the optimal reward, which requires us to train the Soft Actor-Critic agent without any skills on the environment first, which increases the computational effort needed. In Eysenbach and others, they follow a completely different approach. Here, the mutual information is maximized by a separate objective, which includes the discriminator entropy and a so-called importance weight W. And this importance weight here is the clipped importance weight, which is the unclipped importance weight clipped to values around 1. And this unclipped importance weight is reminiscent of a softmax function. It normalizes the expected return, and for those state, action, and skill tuples with a relatively high return, the entropy of the discriminator will have a more profound effect on the weights, and this encourages the policy to learn diverse skills that also promise high returns. Yes. So these three ways of maximizing the mutual information objective are given, and right, the JInfo updates both the discriminator and the actor. And in this table, I've provided a short overview. We have in OSA and others, we have that that there are continuous latent variables in the algorithm, and the mutual information objective also includes the action. And all three approaches differ in the way that this is maximized, from keeping the environment reward out to incorporating the environment reward, and finally by maximizing JInfo alongside the accumulated reward. OSA and others reformulate the reinforcement learning objective. How do these skills actually look like? What does the agent learn? In OSA and others, no, not OSA, in Eysenbach and others, the environment reward was not given during training. So the agent simply learns to behave maximally diverse with respect to different values of the latent variable. And here it uses discrete skills, and here you see for different discrete skills how the agent moves. The agent in this case is a half cheetah, and it learns to move backward quickly, backward slowly. It has different modes of staying pretty much in place, for example, face planting, and it also learns to move forward slowly and move forward quickly. Now, in the original half cheetah environment with the reward, the last two skills will achieve a pretty high reward. And that is the premise that Eysenbach and others give in their paper, which is that among some of these skills, there will be ones that will achieve a high reward. Now, to give an example of which skills are learned when the environment reward is given during training, we have the experiments by OSA and others, where in this case, two continuous skills are given to the hopper, and it learned to map the certain styles of movement to the different values. And for example, for the first continuous skill, we see that it preferably bends the lower knee for low values of the first skill, and preferably stays straight or bends the upper knee for higher values. The second continuous skill, it's hard to see, but it kind of affects how the foot lands and how it jumps. For some values, it will kind of tiptoe, and for other values, it will land very flat. So that was my seminar presentation. Thank you for your attention, and I'm glad to answer any questions.